Dr. Tiamiyu, Dr. Meza, you're welcome.
Thank you very much, sir.
Thank you very much, sir. It's a pleasure being with you guys.
It's our pleasure too.
Oh, it's very much. Wow.
Dr. Casey, Dr. Emmanuel, you're welcome.
Chinese student.
Do you know another international student who is studying biology right now?
But they have gone home. My batchmates, Malaysians.
Dr. Prince, Dr. Boyi, you're welcome.
Yeah, bro.
Dr. Ben, you're welcome.
Thank you.
We will be starting very, very soon, as we are already past 7 already. Good evening, everybody. I am Olayemi Rufai. I am the treasurer of Organization of African Academic Doctors, OAAD, which is our organization. You are all welcome to this great, resourceful, and intellectual gathering. Our main objective in OAAD is to bring Africans together and foster development through technology and innovation. And one great strategy that we have designed to achieve this is through organizing a webinar like this that will enhance knowledge sharing. And our today's resource person will be Dr. Kaunda. Dr. Sakah Kaunda is a postdoctoral researcher and currently based at the Key Laboratory of Medicinal Chemistry of Natural Resource, Ministry of Education, Yunnan Province. He's in the School of Chemical Science and Technology in Yunnan University, China. His research focus is on the exploration of medicinal plants for their bioactive constituents with cytotoxic and anti-inflammatory activities. Africa is actually awash with medicinal plants, as we all know, but a significant percentage of works published by our people is based on crude extracts. Dr. Kaunda has contributed to the global knowledge in his field by publishing his works in reputable peer-reviewed journals. And I think he's got more than 7 publications. He's enthusiastic about natural pharmaceutical chemistry research and well disposed towards teamwork and collaborative initiative in related research areas. Dr. Kaunda is a husband and a father of 1 kid. So please kindly help us to welcome Dr. Kaunda Joseph Sakah. You are welcome. You're welcome. I will be handing over the mic to Dr. Kaunda now. But however, before doing that, please, I would like to state that Dr. Kaunda has made us to understand that this webinar will be interactive. It will be like an interactive session because it will be more of practical. And if you are having any question along the line, please kindly feel free to be typing it into the type box, the chat box, so that Dr. Kaunda will also be saying it and he will be having a conversation or having justice to do with that. So thank you very much as we welcome Dr. Kaunda.
Thank you. Thank you very much, Treasurer. Am I loud and clear?
Yes.
Thank you very much. Yes. Welcome all of you into this presentation. Feel free. And just as our Treasurer said, at any point where you feel like asking a question, please do so. Yes, and kindly keep your questions within the topic of discussion. Yes. So, research in natural pharmaceutical chemistry is an old area of science. You know about the anti-malarial drugs that we use in the market today. The parental structure of that compound. That compound was isolated from a plant, 1978. That is just one example. So plants have contributed much to the area of drug discovery and medicines. As we start, allow me to thank God for unveiling unto us such a wonderful day and giving us this precious opportunity to share my experiences in structure elucidation with you. This presentation is meant to equip us with some basic precursors and ingredients needed in structure elucidation by researchers in this field of study. Allow me also to appreciate very much our president for setting up such a powerful platform to bring all of us together so that we can link up and be able to uplift and edify one another. He said something that older hands helping younger hands, and both hands growing stronger together. There could be somebody here pursuing a degree or a Ph.D. master's in natural pharmaceutical chemistry. And basically, extracting a compound is never a problem. I say, you can bring somebody from the village with no background in education, in chemistry, and just give him instructions, do this, do that, and you'll get a compound. And after getting a compound, what do you do with it? Now, I've said purifying a compound is not a problem. The biggest problem we have is to elucidate the structure of that compound and to know what it is. Hello, is everything okay?
Yes, sir.
Okay, thank you very much. Back home, many of us have tried to pursue this field, but sometimes the highest level we've gotten to is on the crude extracts. Many times we don't even have equipment to provide data. So we get to the level of crude extracts, do activity, and publish papers. And we graduate with degrees, with PhDs. But I've been privileged to go beyond that, to be able to learn structure elucidation and to determine the structures of my own compounds. So in this presentation, we will not focus on extracting the compounds, but on structure elucidation, because I believe that's where the major problem is. Even our professors back home, our doctors, who obtained their degrees in our local universities, most of them, if not all.
Dr. Kaunda, I'm sorry,
Yes.
please. I don't know. Are you trying to share your PPT?
Not yet, not yet,
Okay, not yet. Okay, thank you. Continue, sir.
not yet. Most of them in this area of medicinal chemistry have problems elucidating their structures. So, having said that, allow me now introduce my PPT, share it with you, so we can get into the gist of the matter. Are you able to see my screen?
Yes.
Yes. Organization of African Academic Doctors. So I'll talk about, I said, my experiences, and along the way, I'll also be able to bring along a friend and a colleague, a fellow laborer in this vineyard, also to share with you his skills and experiences. Usually in structural elucidation, you'll find that if you've been working on a particular or some species, you become a specialist in elucidating structures belonging to some classes of compounds. So during my PhD studies, I came across various types of classes of compounds: phenolics, steroidal alkaloids, and flavonoids. Those two are phenolics, tannins. So I will be just giving some basics, and I'll be able to take you through solving a practical problem. I'll show you NMR data of a compound I'm familiar with very well. It was my compound. I isolated it, determined its structure, and we shall learn a thing or two. And I believe that at the end of this discourse, we shall have benefited. Now, what you see before you is just a schematic diagram of NMR chemical shift data of protons. The diagram gives you the range. Are you all right? Someone is coughing. Are you okay? Welcome. If you look at the diagram before you, are you able to see my screen?
Yes, we can.
Yes. So they're telling us here that when you have a proton spectrum from 0 to 12, these are chemical shifts. Usually, from around this region will appear the CH3s, CH2s, and CH4. Now, in this presentation, you allow me to use chemistry terminologies. CH3, we call it the methyl group. CH2, methylene. I don't know whether to write, but I think if you're in pharmaceutical chemistry, you understand me clearly. The CH, the methine, they appear around this region. But you will find that when you have both the methyl and the methylene in the spectrum, the methylene will appear further downfield. Downfield, I mean, moving from 0 to 12, we call it downfield, meaning it will show a higher chemical shift. Reason being, for proton spectrum, are controlled primarily by electron density. The more electron poor a proton is, the larger its chemical shift. So you will see CH3 being closer to 0, meaning upfield, and CH2, the methylene, moving towards 2, away from 0, meaning further downfield, having a higher or a larger chemical shift. As you move further downfield, the chemical shift increases. Now, I'll jump to region 7, around 7 and 8. They say, usually, when you see protons appearing, when you see protons displayed around this region, it suggests that there could be a benzene ring. What you see here is a benzene ring. You can call it aromatic ring. You can call it phenyl group. We say it indicates, it suggests, it connotates that the molecule we're dealing with here could be having a benzene ring. Down there, you see the ketone. We have C connected to oxygen. Being larger, the ester groups, carboxylic group, towards 12. Now, if you're in pharmaceutical chemistry, this is not meant for you to cram. No. You don't have to put this in your head. That will be too much and it won't help you.
Yeah, I don't understand it.
A professor once said that memorizing a lot of chemical shifts is not going to be very helpful. Instead, he suggested that you do practice. By practicing, by trying to elucidate the structures of known compounds, you'll be equipped by certain techniques, certain concepts that will help you. Even finally, when you get a new compound. Allow me move to our next. Now, this is carbon. The diagram is showing us the ranges of carbon chemical shift. Like I said, 0, the reference, and away from 0 towards 220, we are moving further downfield. The chemical shifts are increasing. Why the increase? Okay, you can see here the CH3, the methyl group, the methylene, the methane groups appear between 0 to 60. Between 60 to 80, you see oxygen being introduced. Meaning, when you have a spectrum, carbon-13 NMR spectrum, and you see signals appearing around 20 towards 40 there, then you can start fingering in your mind. that there could be some methyl groups, methylene groups, methylene groups here. When you see signals resonating between 60 to 80, 100 there, you already have in your mind that there could be oxygen or nitrogen attached to a carbon somewhere. Are we together?
Yeah.
Thank you. Let's proceed. Now, having understood something small about it, I want us to go straight into application. I featured here some few compounds that I am familiar with very well. I want us to look at compound 1. But before we get there, let's go to the spectral data. How did we get here? How did we come to the conclusion that what the NMR equipment gave us was this? Let's look at the proton spectrum. If you remember our introduction, when I was talking about regions, the range, that when you see protons appear in this region, it suggests that there could be this particular group, methyl, methylene, methane group. There could be sugar, benzene ring. What is before us is a proton spectrum. You see, we have protons appear here, between 1 and 2. So what comes in your mind? If you're forgotten, you can go back to this. Between 1 and 2 there, CH3, CH2, CH. So when you come and look at this data, you can already figure out that there could be methyl group here, methylene, methane group. At least it is giving some clue. That's why usually when you publish our papers, you say the proton spectrum suggested that, indicated that. And this was confirmed by signals in carbon-13 spectrum that appeared at blah, 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 chemical shift. So look at the region between 3 and 5. We have signals there. Go back to this. And between 3 and 5, we said there's probably oxygen and some other groups apart from carbon. So spectrum, you can figure out that this region possesses some oxygenated carbon signals. Look at the region between 6.5 to 7. Here we learned that it suggests the presence of a benzene ring. But we don't just end it there. When it comes to a benzene ring, there are certain characteristics that the proton spectrum will give us to confirm that surely this is a benzene ring we are dealing with here. Now, are we still together? I hear some noise from somewhere. Moderator, you may help us to cool him down. Just cool him down. Let us proceed. Now, allow me share with you MestReNova. If you are in chemistry, you already understand what this one is. And if you have problem, for example, how to upload data here, but we can discuss later. But are you able to see my MestReNova? Are you able to see my MestReNova?
Yes, sir.
Moderator?
You can. Yes, you can.
Able to see what I'm doing?
No, but we're not seeing your cursor.
Okay, then let me share it. Yeah,
Dr. Kaunda, please, can you make your PPT full screen?
Wait a moment.
And we're not seeing the cursor. But we're not seeing your cursor.
New share, okay. MestReNova. Now, able to see some actions from my side? Moderator, please give me some feedback.
I think it's bigger now.
Okay, okay.
Please, can other participants, please, can we confirm? Can we see it clearly now?
Yes, yes.
Good.
Absolutely, absolutely, absolutely.
All right. Thank you very much.
Okay, thank you.
Thank you very much. Now, this is a proton spectrum that I've just expanded, trying to zoom out. I was talking about the chemical shifts. Using this software, we are able to assign the chemical shifts. We can always come there and you can do it automatic or pick by pick. Pick by pick. That one there. Allow me change the setting, properties, and I want them to have 4 decimal places. So we can pick picks and decimals that are 2, 1, 3, 4. Apply. Okay. So these are chemical shifts. Down this one here. Full spectrum. Allow me get to this full spectrum. And you can do Control K or just come here, pick by pick, like that. I'm giving chemical shifts. Yes, I want to get to that level. So from here, we want to calculate what we call the coupling constant, the J value. It has some significance, which we are about to see. You can do it manually, or we can use the software. Manually, you calculate the difference. Like, for example, if you want to get the J value of the proton here, it's a doublet. You subtract the smallest value here from the largest and then multiply by the frequency of NMR spectrometer that was used to record the spectrum. Here, if I remember well, I used NMR 600. Yes, I'm right. Yes, 600. So, okay, I won't share my calculator with you, but I've said you subtract the small from the larger one and then multiply by, in this case, I used 600 megahertz by 600. And moderator, are you with us? Moderator?
I'm with you, I'm with you.
You should be helping me to do the calculations if you are really with us.
Okay.
Yes. 6.9888 minus
6.9888.
6.9917
6.9917.
we have 6.9917 minus 6.9888 times 600, 1.7. Okay. Using the software, you will do this here and manual. Chemical shift 6.99, then right click, report multiplets. And what you have this J value.
Okay.
Can you see my screen clearly?
Yes.
J value 1.7. We are right. So we're done with one full screen. We have these protons too appearing in the region where we say the Kolbe benzene ring. So here, J value, let me use the software. Right click, report multiplets. Now, we have of this proton here and this. We want to talk about J value and want to give it special attention because of its importance. The J value of this proton in this region is 1.7. J value, this proton pair has DD, double of doublets. It has two J values, a small one and a larger one. You can see the small one is the same as this one, 1.7. The larger one is 8.1. We can do this one too. We check what it is. Singlet. Now, what the protons are giving us here, they are revealing to us that indeed the molecule contains a benzene ring. Now, there's something called substitution that I want to talk about. Allow me share with you ChemDraw and then able to draw a proton, a benzene ring, not a proton, sorry about that. New share. Share ChemDraw. ChemDraw. Are you able to see my ChemDraw? Hello? Magnify.
Yes.
Yes.
Thank you.
Yes, you can see.
Thank you. Benzene ring. Okay. So we have proton whose J value is equal to 1.7. Actually, there was 8.1 and 1.7 has. Usually we write J, we italicize it. And we also have another proton whose J value was just 7. 1.7, I mean, 1.7 has. And there was one. Now, even before we go to 2D NMR, the J values as retrieved from the proton spectrum can already tell us the positions where each proton is on the Benzene ring with reference to a particular proton. So in this case, you can see, let's say you start with the first one, and let's say the proton is here. Usually we don't draw protons like this, but for the sake of this presentation, allow me to do so just for, for your viewership. Now, the next thing I'll be talking about, probably you've heard it before, ortho, meta, para substitution, and how J value will direct you on where to assign each proton. Now, if the proton whose J value is this 8.1.7 is here, the proton adjacent to it, here or here, we call that ortho substitution. Usually, this proton, mistake, allow me. These two protons, they split each other and will appear as double of doublets. And the J value of an ortho substitution is always between 6 to 8, or around 7 to 8. Now, look at this. The proton whose J value is this. And this one too should be 1.7. They are the same. From here, you can tell. Hello, is there a problem?
What time is Annabelle's event?
Hello?
No, I think there's no problem.
Okay, thank you very much.
Yeah.
Based on the J value, you can assign
Oh, where did you get it?
proton
This coordinator, why not tell them to off their mic, please, sir?
And this one,
Okay.
adjacent to it. It could be here or here.
Dr. Kaunda, please,
Yes.
just a moment.
Okay.
Hello, everyone. Please kindly put your microphone on silent if you are not saying anything for now. Thank you.
Can I proceed now?
Yes, you can proceed now.
Thank you, sir. So, the proton whose J value is small, usually between 1 to 2. The reference to this, it means this one. Let me highlight it with red just to. With reference to this one, this proton could be here or here. That is called meta substitution. J value is always small. So already you figured out that there is a benzene ring in this molecule, and this is the substitution system. In chemistry, we call it ABX. That's not important at this stage. Maybe you know that as well. You can find that online, no problem with that. So the fact that we have a proton here already, this one cannot be here. If you put it here, then we could have seen some relationship with this. So it is not here, but it is here. Now, based on J values, you can determine the type of substitution in your benzene ring. So, open. I hope you can still see my ChemDraw, right? Can you see it?
Yes.
Thank you very much.
Yes.
Now, there's a proton here. There's a proton here. There's a proton here. From what I just showed you before, the two protons adjacent to each other. Auto substitution, J value, they have two J values because they appear as doublets of doublets, DD. One J value is bigger, larger, around 7 to 8. One is small, 1 to 2. The other one that is smaller belongs to this position here. With reference to this proton, this has a smaller J value, indicating meta substitution. Now, how did we bring in the methoxy group here, the hydroxy group? Where did they come from? That they belong to this position and this. Already, we've assigned this and this and this. We know. We have that in our mind. from the proton spectrum. I've not even gone to carbon spectrum to know their values, but just based on the J value, the coupling constant as displayed by the proton spectrum, we can assign those 3 protons on the benzene ring. If one is here, the other one must be adjacent to it, separated by 1 bond, and the other one must be on the meta position with reference to this. So let us go to our carbon spectrum and confirm. Let me share with you. I think I'll just go straight to MestReNova.
Please, participants, can we kindly put our microphone on silence?
Yes, that is very good, moderator. Can you see carbon spectrum, some lines? Those of you who are not in chemistry, are you able to see some lines? Are you able to see my carbon spectrum?
Yes,
Moderator?
you can see.
Thank you very much. Thank you. Now, remember we said from the proton spectrum that, let me bring it forward again. When you see signals around 1 to 2, it is a suggestion that there could be methyl groups, methylene groups, methane groups in this molecule. Now, here we have carbon 13 spectrum, depth 90, depth 135. I put all of them together and align them perfectly. Those of you who are in natural products chemistry, '90 spectrum will only give you positive signals of methane groups, CH. Positive means positive polarity. The signals face upwards. Let me just use that terminology. They just face upwards on the spectrum. Depth 135 will reveal to you the methylene groups, CH2. And the CH2, they appear as negative signals. They face downwards. In this data, there are 1, 2, 3. These are methylene groups, CH2. We also have signals, positive signals on depth 135. Usually, the signals that you will see appear in 135, positive signals, and also they appear also on depth 90 as positive signals, and also on carbon 13. We call them methane groups, the CH. You'll find CH in the 3 spectra, carbon 13, depth 90, depth 35. CH2 will only appear on carbon 13 and depth 135 spectrum. The key feature determining the CH2 is not on the carbon 13 spectrum, but on depth 135, meaning you cannot, if you go run an NMR, equipment run data, only carbon 13, it will not indicate you what signals there is CH2, CH3. You have to do depth. Then you have a complete data of carbon. 3CH2. There's a signal here. The signals that appear in depth 135 and carbon 13, positive signals, but do not appear in depth 90. Those signals belong to methyl groups or methyl, meaning CH3. CH3. Now, let us carefully dissect the spectrum before us. You can see this one, 19.1 and 56.5. They have the same features, but difference in chemical shift. Why? Both of them show C3. But why is one further downfield? Go back, remember the PPT. That slide where we said, when you see it shifted further downfield, it suggests that it is connected to something else. It is a CH3, but in this case, it has something else. So for this one, it is connected to an oxygen. Are we together?
Yes,
No.
yes.
Yes. So we have CH3, and we call this one the methoxy group, methoxy, or CH3, the methoxy group. This is just methyl, the CH3. CH3 plus oxygen, now the methoxy group, further downfield. Then here we have CH2s and a lot of CH molecules, CH resonances here. Usually when you see, I'm talking from experience here, when you see CH signals appear like this, and the CH2s, it could connotate the presence of sugar moiety. If you're in chemistry, you understand what moiety is all about. Those of you in social sciences, please just forgive us for such terminologies.
Okay.
Yeah, we are not causing any harm to anybody, but that's how it is. The sugar moiety. And then what should come to your mind is that what type of sugar could it be? Glucose, apiose, rhamnose, xylose, what could it be? If it is glucose, you know glucose has got 6. Apiose, 5. Rhamnose, 6. If you're in chemistry, then you know that rhamnose has got a methyl group also, rhamnose 6. But we don't end there. If it is true that these signals arose from a sugar molecule, then there's some more information that we can pick from the proton spectrum, because there is a region where we call it the anomeric proton signals of sugar molecules. Anomeric, I mean number 1. Every sugar molecule Hello?
Hello?
Hello? Muted?
Yes. Can
Was
you
I
hear
muted?
me?
Can you hear me? Did anyone skip a thing?
I can hear
Because
you.
you told me that I was muted. Okay,
Yeah,
thank you
please
very
go on.
much. Let's go back to our proton spectrum. If you're in this field, I want to focus here. Look at these two. If you calculate the J value, let me go do so straight away. Manual. Report multiplets. 7.8, 7.6. They appear as D tablets, DD, and the J values are bigger, between 7 to 8, 7.8, 7.6. It is a suggestion that we have two sugar moieties in this molecule. There could be two glucose units or glucose and probably a xylose, but not rhamnose, because the anomeric proton of rhamnose appear as singlets, not doublets. So those are some of the key things, little here, little there, that you can arm yourself with. And by experience, you will know that with time as you interact with compounds, with sugar molecules. Now, the proton is telling us here that we could be having two sugar moieties. Let's go back to carbon. We have this region. If there are sugar, two sugar moieties, does the carbon spectrum support that? Sometimes you can literally count 1, 2. Are you able to see my
Yes.
screen? Okay, thank you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe I missed something. It does not matter anyway. But the point I'm trying to underscore is that our molecule has got two sugar moieties. And the resonances in the carbon spectrum confirm that. Now, allow me just to share with you.
Okay.
ChemDraw. Once again,
Dr. Kaunda,
yes.
please, can we ask that is everybody following up to this level?
Yes.
Is there any
Please ask.
confusion
Yeah,
or anything?
please do.
Yeah, we've been following. I'm following. I'm really enjoying it.
Are you enjoying something?
Yeah, it's all right.
Okay,
No problem.
thank you.
Let's go on.
Okay, thank you. We can continue.
Thank you very much. Yes. Now, I've shared my screen with you. Can you see the structure there?
Yes, yes.
Thank you very much. Thank you very much. Thank you very much. Already we had assigned this position, this and this. But how did these two guys come in? Now, we use what is called Hmbc Spectrum. HMBC shows correlations between protons and carbons. If there is a proton here, of course there is. If you check Hmbc spectrum, you find that this proton correlates with this carbon and this carbon and this. But it will be difficult for this proton to show correlation with this. It's quite far. Sometimes they do, but it's quite far. Mostly it will show you this J1, J2, J1, J2, this and this. But because we know this, and we know this, meaning this proton from HMBC will be able to get what carbon to assign to this and to this. But what is the difference between this and this? How did we know that this should be here, one should be here, one should be there? Let's go back to our carbon spectrum and talk about a little bit. MestReNova. Are you able to see my MestReNova? Moderator?
Yes.
You can see it?
Yes.
Okay, thank you very much. Select all. Allow me to do this. Just expand it.
Doctor, we are still seeing the ChemDraw.
Oh,
Okay.
the ChemDraw.
Yes.
Oh, so the
So
moderator
your cursor is on the ChemDraw.
The moderator is not following the
The
presentation.
moderator
Right?
is a social scientist, so he doesn't really know ChemDraw and
It's all right, all right. We
I'm
understand.
sorry, please.
Oh, it's okay, it's okay. Don't mind, don't mind. Don't mind. Yes. Able to see MestReNova now?
Okay, yes.
Thank you very much.
Yes, we can see it.
The signals on the carbon spectrum that they only appear on carbon 13, not on depth 90, not on depth 135. We call them quaternary carbons. Carbons with no hydrogen on them. But why? One is 133, 147, 149. The one that is upfilled, meaning smaller chemical shift, that's 133, probably is connected to another carbon atom. But the ones that appear further downfield could be connected to hydroxy groups, the OH or OCH3. You know, if you want to get deeper now into the chemistry of it, you'll be talking about electronegativity of oxygen, electron withdrawing effect, all that. But that's not important here. That one you can read online. Now, I need to share a screen. Share a screen. Still on that. This proton here. And okay, let me just do this. You can expand this right here. What you have is Hmbc spectrum, giving us correlations between proton to carbon. You find protons in the horizontal plane, carbons vertical plane. If you want to know the signals that appear around a particular region, they appear around that place, you'll see Hmbc giving you some hints. For example, look at this proton here. It's a proton. And look at this signal. These two guys. This proton relates with these two carbon signals, meaning they're in the same place. So we are able to assign each ring based on Hmbc. At least we can tell that no, these particular signals belong to this region. These ones belong to this group, belong to this group. But then now you have to do it to finer details to be able to finally, let me share with you ChemDraw. Share. Can you see my ChemDraw?
Yes, I know this.
You can see it.
Thank you. Thank you very much. Thank you very much. There's a carbon here. Carbon. You will differentiate or assign this respectively depending on this proton. Why am I saying so? Because this proton will give you from Hmbc correlations with this and this. But you already know this. You determined it from the proton spectrum. So the next one will be this, and we know this too. And this proton will show correlations, mostly show correlations with this, and this. We know this already. Already we've known this from this guy. They can assign this to. But how did you come to assign the methoxy group to this carbon? Hmbc. Are we together? Are we together?
Yes.
Now, we have 3 quaternary carbons. 1, 2, 3. Already we've assigned this from Hmbc. You'll see this proton correlating with this carbon. But how did this guy come here? Again, from Hmbc, you'll see these 2 protons correlating with something that is not part of the benzene ring. And we said, what at 3 being small, it indicated to us that there could be a carbon to carbon linkage. And you will see from Hmbc clearly correlation between this proton and this and this. And considering that this 2 is a proton, you'll see this proton correlating with this carbon, and this carbon. Yes, but it is a CH group. But how did OH come in? Because this OH, you don't see it drawn that there's an OH there. Based on the chemical shift in the carbon 13 NMR data, the value of that will appear between 70 to 80 larger value. Then we can tell that no, This one being big this way, meaning it is further downfield shifted as compared to other methane groups, other CH groups. So you say, probably there's an OH. Let's put it there, OH group. And because you've known that this one, there's a proton, then now the next thing that comes to your mind, if the next is a proton, then proton COSY should help us. Then you'll go to COSY. Okay, I don't have to really bring up the spectrum. Let me just talk about this structure here. COSY correlation. I mean, proton COSY. You will see these two protons correlating. If you don't know how to, like analyze your data, COSY, how do you tell that this proton correlates to this? What do you do? How do you observe it? That now we can do in details later. Yes, because I know from this discussion, I'll get some interested people, because this discussion is for everybody. People from social sciences are here, people interested in political things, analyzing the situation between President Museveni and Bobby Wine are also here. So, but after this, I know I'll get interested people. Then you can now sit in detail and talk in details about structure elucidation, put together all the carbon signals and their protons as exhibited on HSQC, and be able to start from scratch, dot to dot, and come up with this structure. Now, I had said that the proton spectrum suggested the presence of two sugar molecules. I found out that one was glucose, one was aqueous. But then how to tell again the linkage? Because now you have aqueous. This is aqueous. This is aqueous. You have aqueous. You have glucose. You have this ring. The interlinkages, how are they connected to one another? Hmbc. The fact that this glucose unit is connected to this ring at this position means the anomeric proton of glucose, this proton here, there's a proton here silently from Hmbc, that proton showed correlation with this carbon signal. Are we together? And the anomeric proton, anomeric means number one, proton of aqueous, showed correlation with the carbon 6 of glucose, the CH2. Usually, let me say this before I forget, when carbon is connected to free hydroxy group, the signal appears upfield, meaning closer to zero to the reference. But when there's a substitution, this was OH, but glucose came during purification, let me say so, and connected there. This signal will appear further downfield shifted, larger. This one will be larger than this in carbon 13 NMR spectrum. This carbon will be larger than this. Larger means appearing further downfield. The same, this one too. Let me remove this. Glucose as it is, like this. CH2 here will be around 60, 61, 62, 63. But where there is substitution, meaning there's a loss of that proton. You know, oxygen is electronegative. Now, when you remove the proton, it becomes more electronegative, further shielded away from the reference point, meaning the chemical shift of CH2 here will appear downfield, 67, 68. So those are the key things that when you see, will tell you, no, yes, there is glucose, but I think based on the larger chemical shift of this carbon, there could be a substitution. Any question up to that point, please? Any question?
Is there any question, please?
No, we're
Any question, please?
Yes.
Okay.
Can you hear me, please?
Yes, we can hear you.
Oh, okay. So, I'm not sure if you are getting to that point yet. This glucose, at the point where it binds to the methane proton here, you have beta configuration here, right? Hello? Hello?
Dr. Kaunda, yes, we can hear you.
Okay, I'm not sure if you can hear me.
Okay.
Hello, Dr. Kaunda.
Dr. Kaunda. Hello?
Dr. Kaunda, please, we cannot hear you. In case you are talking, we cannot hear you.
I think his mic is muted.
I guess you have to call him directly. I don't think.
Hello?
I'm trying to call him now.
Hello?
Yes.
Can you hear me?
Yes.
Yeah, what I'm saying is that every time you try talking, I get muted automatically. I don't know why.
Oh. Okay. The person that is asking the question, can the person try now?
Yeah. Yes.
Everybody's muted. Hello? Hello?
Hello?
Okay.
Okay.
Please
Dr.
allow me to say
Kaunda.
something. Allow me to say something.
All right.
I don't know. It the system keeps telling me that the host has muted you. So I think, I don't know, every time you're talking, I get muted.
Okay.
Okay, finish.
Yeah.
Finish.
Can we try?
Finish.
Can we
Maybe
try
she
now?
just finish.
Yes, please ask the question now, please.
Okay. So, thanks for this presentation so far. I just want to quickly ask this before it skips me.
Yes.
So, this glucose is connected to this methane proton here.
Yes.
So you have a wedge bond here,
Okay.
right?
Now, can you see my glucose?
Yes, I can see you. So I'm just saying.
Yes.
So you have the
Can you
anomeric.
now talk like 1, 2, 3, 4, 5, those carbon numbers, so I can hear you clearly?
Okay. So
yes.
I'm talking of the A glycone here.
Yes, the glycone here. Yes. Yes, yes.
So
The
at this
yes.
age, all right. So you have the numeric position, right? Is you have
Yes.
an eta linkage, right, connected to the methane proton of that is
Yes.
carbon C on the linear chain, methane proton, right?
Yes.
So this wedge bond, how do you differentiate it on the NMR? You have two wedge bonds here, right?
You're talking of, yes, I can see you're talking of the alpha bond, right?
The beta, actually.
The beta, this one here, this one, right?
This one and the other one, yes. This one and this other one, yes. You are pointing, yes, you're correct.
Yes, the alpha, because the proton being silent there is beta, okay? But this is alpha, okay? Now,
Sorry, I think you don't get, you're not on the, okay. Let me come again.
Yes.
This, you are talking of the alpha beta is with respect to glucose, not with respect to the A glycone.
This is the glycone,
So,
right? You see the OH,
yes.
the hydroxy group, and this
Yes.
one here, the bond.
Yes. Okay.
Alpha.
So this bond,
Alpha.
this bond you are touching, this bond you are
Yes.
touching.
Yes.
So how do you differentiate it from the dash bond? This is a wedge bond.
Yes. So we call it the alpha. Okay. Alpha configuration.
I mean,
okay. Now.
Okay. Yeah. Okay.
Now, on the carbon spectrum, you'll not see that. Sometimes in certain structures, based on the chemical shift of carbon, you can say this is beta or alpha configured. But for this type of structure, there is an experiment we do called headlock. Are we together?
Okay.
Yes.
Yes. You know, usually HMBC will give you proton to carbon. But there is a carbon here, carbon here, carbon here, carbon here. Now, please, moderator, help us mute that guy, please.
Who's the person?
Can I proceed? Can you hear me?
Okay, yes, please.
Yes. What we're talking about is called relative configuration, whether it is beta, alpha. Now, we do a certain experiment, and you will see that experiment will show you correlation between these two. There's a way in which when the J value is in a particular region, then we can conclude that the proton there is better configured. The proton is better, then this automatically we use alpha, we call it alpha configuration, alpha and alpha. Are we together on that?
Yes.
Okay.
Yes. Now that is now very advanced, you know. That's a very advanced level of structure elucidation, because you have to get to the point of determining relative configuration and also absolute configuration, depending on the type of structure. Now for this one, I had to do the relative configuration using headlock, and also ROESY spectrum has a big role to play here. This proton, usually when you analyze the ROESY spectrum, when you want to know that the proton is either alpha or beta with reference to a particular proton, you always see correlation on the ROESY spectrum, meaning they are in the same direction. If one is better, then that too is better. If this alpha, that too is alpha, because you see them correlating on the ROESY spectrum. So those are the two spectra that I used to determine the relative configuration of this position and this position. Am I clear? Have you gotten something from that?
Yes, yes.
Thank you very much.
Thanks.
Any other question, please?
Any other question, please? Okay, I think we can continue.
Okay. Now, I think in passing, I mentioned HMBC.
Dr. Omeza is raising his hand.
Okay. Please allow him to communicate.
Okay.
Yes.
I think,
Dr. Omeza.
yeah, please, can you hear me, sir?
Yes.
Okay, thank you very much, Dr. Joseph. Please, I want to know if there's any significance with regards to the signal strength of those spectra, or it is just the position that is important, the strength is not important.
Come up again,
Hello,
please.
sir. I mean, the NMR spectra for the carbon and the hydrogen, does the signal strength have any importance at all, or it is just the position that is important in elucidating the structures?
Now, the strength, like you were talking about the chemical shift, that was meant by signal strength, right? Larger
No, the
chemical
height,
shift.
the height, you know, I discovered that they are not all the same heights.
Oh, you're talking of
Does it
these
have,
things. Oh, no. This one is just, for the convenience of drawing the structure.
no, I'm
It's
not talking
the,
about this structure, sir. I'm talking about the spectrum.
Oh, okay. Let me bring my data here. Allow me to share with you the screen.
Hello?
Oh,
Yeah, I think he wants to share the screen with
Okay.
you.
yeah.
Okay.
Allow me to do it. Allow me to do it. Yes. Can you see it?
Yes, I can see, sir.
Yes.
So I noticed that the height of all the peaks are not the same. Does it have
Yes.
any importance at all, or it is just the chemical shift, the position that is important in the elucidation of the structures?
Yes. Usually, sometimes when you consider, say, the methane signals, the CH3,
Yes, sir.
like the OCH3, you will see it always longer than the rest. It appears, should I use the word, it's longer or taller? Taller?
Yeah, taller.
Yes, taller, Yeah, because in the equipment, the way it resonates with reference to TMS, or the way, you have OCH3 and another one, CH3, and carbon signals without protons. The way the signals are being displayed by the equipment are never the same. But it is not a serious issue. It can be ignored. Yes?
Okay, sir.
Yes. So the most important thing, as you said, was the chemical shift, that value. The
Okay,
height
sir.
is not a major factor when it comes to structure elucidation. But you
All
will
right.
always see the methoxy group, the OCH3, appearing quite taller than the rest. It's no big deal. It does not mean, that we have 2 in 1. No, it's just one signal.
Okay. Dr. Kaunda, Dr. Teddy said he's talking about the integration of the peaks. So I don't know if you are in line with that question also.
No, that has nothing. No, integration is in the proton spectrum.
Okay.
Yeah.
So, and also because of time factor, so maybe you may want to continue with your presentation, then we will collect all the questions. And we are going to talk about that during question and answer.
Okay, if you look at my PPT, actually, I have done with my presentation.
Oh, okay. Okay.
Yes, that's why I asked for questions to come.
Okay, okay. All right.
Yes.
Then we can continue.
Yes.
We can continue then.
Should I continue or pick some few questions?
Yes, you can continue with the current discussion you are on with Dr. Omeza.
Okay. Dr. Omeza, come up.
Okay.
Now, can you see my ChemDraw, please?
I think it's the other one.
The MestReNova, okay?
Yes, this is the ChemDraw.
Can you see this one now?
Yes.
Yes. The question that that colleague brought forth concerning relative configurations. Structure elucidation does not end here yet. You can see we have 2 sugar moieties. Remember, we could be having beta D glucose, alpha L, whatever, alpha D glucose. So, how do you then analyze and come up with the appropriate configuration and conclude that this is beta D glucose, alpha D glucose, alpha L rhamnose, beta D aqueous. This sugar, this is aqueous, 5-carbon ring. There is something we do, acid hydrolysis. During my PhD, I remember I obtained a lot of compounds with several sugar moieties. If you're familiar with steroidal alkaloids, you have glucose here, xylose, rhamnose. So I did a lot of experiments on acid hydrolysis to determine the configuration of each sugar moiety, whether it is beta D glucose, alpha. You have to do that. Acidic hydrolysis. Also, depending on the chemical shifts of carbon and the J value of anomeric proton, you can always tell when the glucose is beta D, beta. Usually, the proton, like we saw previously, J value large, around 7.8. That is a confirmation of being better configured, meaning action orientation. That is something else which I don't want to go into, but let's just talk about this. We have got action orientation, equatorial orientation. When the proton is action with reference to the hydroxy group of glucose 1, you see J value is larger, chemical shift is larger. But when the proton is equatorially aligned with reference to that, then the J value of the numeric proton there appears small, very, very small. And you can tell this is alpha configured. Whether it is D or L, then we do acidic hydrolysis. And we confirm with authentic sugars. You buy authentic L-glucose, authentic D-glucose. And after doing acid hydrolysis, then we run DC mass gas chromatography. Now, depending on the retention time, if the retention time of D, the original D-glucose, is closer to, the retention time of our sugar, our molecule, then you can say, no, this is D. That's how we do acid hydrolysis and confirm. So if you read many articles, like in fact, almost all my papers I did acidic hydrolysis. It's a simple procedure. But I remember I was so a little bit apprehensive before I started, because I was wondering, acid hydrolysis, you're boiling something. So I thought this thing could be dangerous, but along the way, I developed some experience and was able to navigate my way throughout that experiment. So that is how we determine the exact configuration of the sugar moieties. Are you getting something? Even without a question, are you enjoying something?
Yes. Is there anybody with any question?
Yes, sir. Please, I'd like to ask a question, sir.
Please
okay.
Sir, please, before you started your presentation, you said your professor told you that the only way you can understand is by practicing. So for some of us who don't have access to the NMR machine, are there, available data that one can use as self to kind of practice before having actual access to the machine and real data of yours?
Yes. Now, there are published articles, okay? Published papers already. I remember when my professor was teaching structural elucidation, he could call me to office and use a known compound in a published article, and we could follow that, bit by bit. This is like this because this is like this. This is this way because this is this way. When you put this guy, put this here because of this. So literature data is very, very critical. Okay? Even for me to determine that this is a known, okay, it is now known, but when I did it, it was a new compound. I had to do it with reference to the available data. Okay? Hello?
Yes, sir.
Yes. So we may not have the equipment back home, but if you just want to read, just for the sake of reading and grasping something little, just take in high school or primary school, you could revise past papers in preparing for exams. Past papers. This past paper can give you some information about the exam that is coming. So we use known compounds and just try to follow how the structure was determined. And with that, little by little, you amass something, you deposit something into your system. All right?
Okay. Dr. Tosin asked a question.
Yes.
She said, please, can you elaborate more on COSY data and NMR data?
COSY. Okay.
Yes. Hello?
Hello. We are there, right?
Yes, yes.
Proton, COSY, right?
Yes, the message is in the chat, box.
Okay. Let me open the chat box and see. So I see.
Yes. Can you see it?
Tosin is talking about, please elaborate more on COSY data. I think, okay, she's talking about COSY data. That is the most important thing there.
Yes,
So
and NMR
is
data, yes.
NMR is everything. Now, let me just open COSY spectrum. This is it, right? Allow me to share with you. Can you see my screen?
Yes.
Yes. What is before us is a COSY spectrum. Proton, horizontal, proton, vertical. COSY indicates proton to proton correlations, how they relate, usually from one proton to the next, adjacent to each other. If the two protons adjacent to each other, you're likely to see cross peaks in the COSY spectrum. Now, allow me go back to the structure and explain something. ChemDraw. Look at this. Are you there?
Yes.
Please?
Yes.
Have you seen what I've done there? Okay, not do this. Okay, understand, no problem. That is okay. Now, there's a proton here, and this is methyl group CH3 protons too. In the COSY spectrum, you're likely to see correlation between this proton, and this proton. Now, let us go back to our COSY and find it out.
Okay.
Yes, allow me to just share with you. Share again. MestReNova, share. Can you see my MestReNova now?
Yes.
Just expand. When you look at, okay, cannot bring back the structure, but at least you have the structure in your mind, right?
Yes.
Yes. From HSQC, you can align, you can, assign each proton to its respective carbon signal. Now,
Hello?
Yes, can you hear me?
Oh, okay, we can hear you.
Yes. This carbon, you'll find it is 29.9. Its proton is 4.41. Now, from here, how did you determine that next is also is CH? Because already you have a proton here, check from COSY spectrum if that proton correlates with another proton. It is 4. The chemical shift of this proton is 4.41. Let me share this screen. MestReNova, share. Let's look for along the diagonal. You will look for 4.41. 4.41. Yes, it's around here. Let me expand it more. Expand it more. No. Let me include this in the expansion too. Okay. Now, along the diagonal line, look for where 4.41 is. But is there. Then, the cross peaks. Can you see this line? What I mean by the cross peak, right? Can you see this guy here?
Yes.
You see? Then what's the value? 3.88. When you go to HSQC, you will find out that 3.88 is the proton belonging to carbon 83.8 chemical shift. So that will tell you that, oh, so these two carbons are connected. This 79.9 is connected to a carbon that resonated at 83.8. And from here, just follow it. Reference, this is 3.88. If you check closely, 3.88 somewhere there, and then follow this line, you can see here. Oh, so again, it is connected to 1.08. 1.08, the proton belonging to the CH3 group is the methyl group. So it means there is a linkage all the way from 29.9 to the CH3 group as confirmed and ratified by proton COSY spectrum. Right?
Okay.
Yes. Any other question?
Okay, yes. There's another question. Say, please, can the presenter talk a little about extraction and purification compounds? For example, phenolics.
Okay. Now, when doing extraction, talk of phenolics. What I know about phenolics is that phenolic compounds, they are very polar. Okay? They are very polar. And the basics of extraction is that when you have a crude extract before you, you always start by doing TLC, thin layer chromatography, just to be able to find out what kind of systems will be most suitable to isolate your compounds. Like the compound I've just presented, that's a phenolic compound. It belongs to the phenolics, the phenols. I have tannins too. Those are heavy, large molecular phenolic compounds that are very, very polar. So you will find that in your laboratory, you will use high polar solvents to extract and purify phenolic compounds. Mostly from my experience, in the lab, we have, we call it, when you want to do coloration, maybe you do TLC and color, you want to color, there is, how do you call it? We use for, even before you develop the color, when you're now doing your TLC, you know, we use benzene system, formic acid, and ethyl formate. Sometimes we use chloroform, methanol, water solvent, but that system is usually not good when dealing with high molecular phenolics, like now tannins, polyphenols. We use benzene, formic acid, ethyl formate system, and use iodine system to color it, to be able to observe, you know, the development of your spots in the TLC plate. And my experience too is that when doing HPLC, you have heavy phenolic compounds, you always acidify the water so that your peaks can be well displayed, well magnified. You know, when you acidify the water, actually you increase its polarity also. Yes, so that is my little experience with extraction and purification of phenolic compounds. And when you submit it to HPLC, from my experience, you find that you will always elute them using a large amount of water. You know, water being very polar, that means you use little amount, you use little amount of organic solvent and more of water to be able to separate or purify your compounds by HPLC. Yes. Also, I did not talk about columns. Usually, phenolics, we use more of reverse phase columns. You know, silica gel, that is from less polar to more polar. We call it normal phase. But here I'm talking about reverse phase, where you start eluting from high polar to low polar. So for reverse phase columns like MCI, ODS, Cefadex, we use methanol, water system in most cases, where you start washing. That's what I mean by elution, eluting with water. Then you can increase the percentage of organic solvent, methanol. As you're reducing water, you're increasing methanol, meaning you started from high polar to low polar. You know, methanol compared to water is more polar. Yes, so we use a lot of reverse phase columns when purifying phenolic compounds. That is my little experience about extraction and purification. Phenolics.
Okay.
Thank you very much.
Thank you so much. And okay, we will be taking one last question before rounding up, and it's already written here. He said, Dr. Omeza said, how expensive is this data, and can it be commonplace in Africa soon?
Which data? Huh?
Yes.
Come up again?
Yes, Dr. Omeza.
Yeah. Chat. Okay, let me. How expensive?
Sorry, I have a question, please.
And can it be common?
Yes.
Commonplace. What does that mean?
Maybe like, can it be popular? He said the NMR, like maybe can it be popular or general in Africa?
Yeah, that is our prayer, that, you know, we may have these equipments back home. We may be able to explore our natural habitat and produce this kind of results. They are there, but usually this kind of data, sometimes you find them readily available online. Yeah, but mostly, like we use Science Finder that most of our institutes back home do not have. When you're doing your PhD, you need reference, you need literature data. Yes. So, and the ones that are readily available online are not adequate, not sufficient to provide with the data you need, to, yeah. But
I have a question, please.
Okay, someone is trying to ask a question.
Yeah, thank you, Dr. Sakah. Thank you for your time and the coordinator. I'm Hayo. My question is this. Most laboratory, if you are doing natural product isolation, actually many compounds have been isolated from plants. So the chances of you getting a new compound is very, very slim. So, and for some of us, it's more or less like a requirement to get almost new compounds. So, possibly, do you suggest any techniques to target, because so many Chinese have published a lot of papers, known compounds. So it's kind of very difficult to isolate a new compound. Could you suggest a possible way to, maybe a more careful way or something? I don't know. That's my first question. And then my second question is this. For the known compounds, if you notice NMR, they have library, right? And this library, most is attached to, for example, each institute like CAS, UCAS, they have their library and all sorts that is attached to, what's the name of this library again? Oh, I forgot the popular library acronym. NITRA or something. What?
PEB.
Yeah. No, there is another popular one. It has a website. So my question now is this, that the known compounds, so you have the password to the library, you have everything. Do you need to still confirm from the literature of the already published work? Because for me, I'm working on the Chinese herbs, so many Chinese herbs. Most of these plants I'm working on are written in Chinese. So it's kind of very difficult for me to even confirm if my known compounds is already been published or something. I don't know how you are able to identify your known compounds. If it is unknown, at least we could do different like Hmbc COSY relationship to find out if it is a new compound. But in a case where it is known and you need, I don't know, maybe you have another software or a system for you to confirm those known compounds, because the known compounds, you don't need to do Hmbc, you don't need to do COSY relationship. Just do your proton NMR and your carbon 13. You should be able to figure out that, okay, these are already known compounds. So maybe if you could guide, that would be good for me. And then if you have any textbooks that can be very useful in this spectral interpretation, that would be good, because I noticed nobody can say I know all the spectral analysis. I don't know. So if you have some textbooks too, if you could share with me or with us, that would also be very good. Thank you for your good work. Thank you so much.
Yes. Now, when you are doing, when you are purifying your compounds, there are those particular compounds that are very easy to isolate. You look at it and you feel ecstatic about it. Your energy is elevated. You're very happy about it. The peak is beautiful. This is coming. Mostly you'll find out that those are non-compounds.
Exactly.
And sometimes you see some ugly looking peak. You wonder, is this going left or right? You know, and it is very small, and you know, it looks stubborn. Pay more attention to such. Okay. I remember in my PhD, I obtained 20 new compounds.
20 new?
Yes.
Wow.
No, before you celebrate, I know people who obtained 100 new compounds.
Wow.
Yes. Well, I 10 new ones came from a medicinal plant that came from Kenya, and I got the rest
You
from
work with Chinese plants, huh?
Yes, I got some from Chinese plants. Okay, Chinese plants. So, and I would want to say that getting new compounds has a lot to do with the luck.
Yeah.
It's not even hard work. It's luck, my brother. When the favor of God is upon you. Because, I mean, sometimes your professor gives you a plant that people have worked on for years and years. And you work on it again, or a plant from a genus that has been worked on. You do it to the finest details. You do it and you do it, you know, smartly doing it. But at the end of the day, you have 500 known compounds. But you take this plant and you start doing it within 1 month, you've just, you know, done just one fraction of the whole sample. And already you have 6 new compounds. So do call that hard work or that is luck? For me, I shall say that is luck. That's just luck. And the main thing when doing a purification, focus on minor compounds, those small peaks, those ones that appear difficult to isolate. Focus on them. Okay?
Yeah, thank you.
Yes. Yes. And number 2, never ever throw any sample. Never ever, says throw, discard. Never ever discard any sample until you publish your papers and graduate and get to the airport. On your way home, then you can send instructions that please, now that sample, you can now discard it. Never discard any sample. During my PhD, I remember I almost discarded the sample. It is that sample, I did it in my last, when I was almost graduating. That's why I got 10 new compounds from a sample I had kept aside. I was almost discarding. I said, this is not helping me. Let me push it aside. Just let me keep it somewhere there. You know, I got 10 new compounds from that fraction I almost discarded. Okay? Even when you are struggling with that sample, along the way during your study, you will gain more experience. And when you come back to that fraction, then because you've accumulated some experience in the course of your study, you can now come back to it. Never discard anything. Many students do so. Washing everything out, I don't need this. No, you need them. As long as you've not been conferred your degree, you need everything there. Keep everything and focus on minor compounds. Even if a sample is appearing stubborn, you try to dissolve it in methanol, nothing is happening. Chloroform, water, acetonitrile, whatever, ethyl acetate, petroleum ether, keep it. Always keep it. Okay? The library, we have Science Finder. Let me share my screen with you. Are you seeing my screen again?
Yeah, yes, sir.
Can you see where my cursor is on the ChemDraw? Can you read it?
I can't find your cursor. Oh, yes, 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 yes. I saw search.
Search. Click it. What this? Can you read this? Search what?
Yeah, SCI Finder. Yeah, yeah. I have
Yes.
the password. Yeah.
Yes. Let me say exact structure. Okay. Search. So this is structure I've drawn and it is published. So Research Finder will give us the data. Okay. But for me, from my experience as a young researcher, I'm a young researcher. Actually, I don't arrogate myself, the monopoly that I don't say that I know this. No, I'm sharing my experience with you as a young researcher. If you are there and you want to learn structural elucidation, always do 1D and 2D NMR because you don't have experience. You can't just look a carbon skeleton, carbon NMR data and say, no, this is this. This should be this compound. No, it is not easy. Some of these professors and the Chinese, because they have done this thing for years and years. We were born, we found Chinese doing structural elucidation, developing their medicine from their plants. They can look at a carbon skeleton like this and say, this compound, this is called oligosaccharide, whatever it is. Just by looking at carbon skeleton without doing 2D NMR. And you came from Africa the other day, you look at the spectrum, you're wondering, what kind of thing is this? You cannot. So if you want to learn, always do 2D, and let someone help you, guide you on how to elucidate the structure. Even if it is known, don't just do carbon and then throw it away like that. No, you will not learn. Because the skills that you will assemble into your mind after learning how to elucidate structures of known compounds, those skills will help you in determining the structures of your new compound. Okay? Hello?
Yes, I'm with you, sir.
Thank you so much. So,
thank you so much.
Let me share Mozilla Sans Finder. Can you see my Sans Finder?
Yeah, yeah.
Yes, so I'm searching. You've drawn the structure, you're searching. Most similar, okay. No. Sans Finder sometimes can mislead. But anyway, we have it here. So my structure is in a published paper and the data is not coming here. Okay. Yes. So when you search, it will always give you, similar compounds that have been isolated and published. Yes. If it is known, it will show. If it is new, it will indicate to you. That is so, like you just said, you have your account with Science Finder. So there's no need to worry. But don't just depend on carbon spectrum. You will not learn. Actually, these days, we have got carbon 13 data. Library is there, where once you have your carbon data, you can just enter their carbon 13, all the chemical shifts, enter them, and then search. And it tells you these carbons belong to this compound. But yes, it has given you the compound, but you don't know how it was determined. So I stress on doing 2D and learning. Actually, when you're following now a known compound, it's where you learn things. That's the best way for a young person like you and me in order to learn. Thank you very much.
Okay, thank you so much. Yes, Dr. Teddy, you've been raising your hand. I don't know if you have something to say before we round up.
All right, just a question. Thank you so much for the presentation. It was quite enlightening. So, from your experience, do you advise to get new compounds? Do you advise people to come to China or to, especially a place like China? Do you advise them to come with our indigenous plants? Because I know that some plants, no matter how much the Asians have reported new compounds, we still have. I think Africa still hosts, a reservoir of some very, very interesting natural products. So,
Yeah.
do you suggest or do you advise that when people are going to China, they should have, even if it's just say 500 mg or 1 gram of a plant material that they know that is indigenous to Africa, and they can just work with it over there?
Yes, mostly it works. When you bring a plant from home, we've not done a lot of research on our plants. Yes, yet we have an avalanche of medicinal plants. But even today, Chinese are still working on their medicinal plants, and they get new compounds every month on Chinese medicinal plants. They get new compounds. Even now, I'm working on a Chinese plant. I started, I think, already I'm getting new compounds. So you may carry something from home. Yes, the probability is always higher getting new compounds from an African medicinal plant, but it's not a guarantee. It's not a guarantee. Also, the problem is that it's not easy to get or to bring in large quantity of plant material from back home. It's not easy. You cannot come to China with 1 gram and you are serious about getting new compounds. No. 1 gram is too small. You need, because most of these new compounds, sometimes they appear as minor. Yeah? They're just small inside that plant. Small. So you need large quantity. But when you are lucky enough to find a plant,
1 gram of 1 gram of maybe methanolic extract that you freeze dry.
That is small.
It's small.
That is still
It's small. It's not.
That is
It's not
small.
useful.
That is very, very small. Yeah, that's very. In fact, when I'm doing HPLC, I use 1 gram to run on HPLC. That means I have purified. I started from 10 kilograms, purified. And now I have sample to run on HPLC. Yes, so 1 gram is very, very small. You may get compounds, but the amount may be too small, even too small to run on an NMR machine. Because if you're not privileged, like I was to be in some top institutes where they have powerful NMR machines, 800 megahertz, where you can run 0.3 milligrams of your compound, of your sample. Yeah? Some places you only have an NMR machine, only 400 megahertz, 600 maybe.
Yeah,
the highest.
400, 600.
Yeah, 400, 600, So you need large amount of sample. Yes, large amount of sample to run on 400, 600. But for 800, even if it is just small, 0.5, 0.2 milligrams, you can run on 800. But most institutes in China don't have that, don't have such machines. So you need large amount to start with. And along the way, yeah, that's what I can advise on. Even Chinese, The reason why they discourage us from bringing plants back home, because they know you will bring small quantities, which won't help. In fact, I struggled getting samples from Kenya. I asked for samples to be brought to me, and more than people brought me samples from Kenya from that plant. But for the Chinese, it came once 10 kilograms, because you are here, you are in the country, and obtaining plant material is easier. So when luck comes your way, you get new compounds. When you are not lucky enough, you get known compounds. But never ever give up. Always try from this plant to this plant, this plant to this plant. You'll find new compounds and publish a good paper and graduate. Because there's a beauty, the joy, the satisfaction that comes when you obtain new compound. You feel like flying, but you're just walking. You feel the following day when you wake up going to the lab, you are encouraged, you are refreshed, your energy is rejuvenated. You obtain new compounds. The joy is unspeakable. But you're every day working hard, waking at 2 a.m. and non-compounds, it is somehow a discouragement. Okay. Yeah,
sorry, let me give some experience from a friend of mine regarding the last speaker. This colleague of mine is from Nigeria, and we were thinking of contributing to Nigerian plants isolation and natural products of a thing. But when we got here, Chinese herbs generally, they are very difficult to isolate. I don't know if they have some Chinese idea about it, but this my friend, he worked with Chinese herbs, and he was unable to isolate even a known compounds. So he sent for plants from Nigeria. Unfortunately, he sent about 10 kg. He paid so much amount of money for DHL or something, and he got here, the postal service, they seized it. The professor went there, they didn't allow the professor. So much effort to retrieve the plant, because in Nigeria, you will just see that for a PhD degree, you may only need about 5 compounds. Once you identify and isolate stigmasterol and some other known compounds, and you do some biological activity, you can get your PhD. But now, so many compounds are still unknown, even on plants that people have gotten PhD on. But here you have to drain the whole column, wash. And now, because it's a Chinese herb, you don't know whether you need to speak some Chinese words to the to the compound. So it's so difficult, and this guy is already frustrated. Even me, I was thinking of sending plants, because I worked with some Chinese herbs. My supervisor bought them from Tabao. Immediately I saw the plant, I said, I cannot work with plants from Tabao. He said no, that they've been using it. I said, Tabao, I can't work. Sorry for laughing. At the end of the day, I noticed that the plant is filled with glucose, carbohydrates. They've done so much purification on the plant that you can't even be able to isolate. All what you've been isolating is just sugar, something that not really compounds. So we were all confused, and I convinced him that these plants are not really, they've mixed it. He went ahead to contact another Tabao pharmaceutical company. They sent him another plant. When we compare the same plant, we compare their TLC. They are different. So at that point, he was able to say, oh, you are right. And he got me a fresh plant. But the fresh plants he got were very expensive. I couldn't even get up to 10 kg. So I'm so slim with my work. And I'm just praying to get some pure compounds and unknown compounds so that I can graduate. So it's advisable to work with fresh plant, even if it is something you need to go to the village or anywhere yourself to get it from China. And if you
Yes.
want to bring plants from your own country, already do the extraction, get the extract.
Yes.
Sometimes
Yes.
you can
Yes.
face some difficulties from flight or something. You can get this silica gel to mix it. It will be like your normal gari, your normal
Yeah.
powder food. Put it in your traveling bag. If you are lucky to, you can run out of luck. But this is the best way, which many of us who came here we didn't do. And
Yeah.
COVID didn't allow us to go back home to do something like that and bring.
Did,
So this is
did you
my
try?
advice.
Did you try? Ayo, did you try quarantining it at the airport?
They did. I think they did. They didn't. I think it's because of this COVID of a thing, and they
No,
advised that they will.
before COVID. Before COVID, they would allow it. So if you quarantine it, yes, if you quarantined it, so you when you fly, when you land, then every other thing just goes ahead. Then when it gets to the airport, they just clear it and they deliver it straight to you.
I think it was DHL. I think this postal services. It was DHL.
Yeah.
So DHL
Yeah.
checked at this border here at the point of giving it, and they noticed that it wasn't something they. I think it has been prohibited, or maybe because of COVID or something. So they didn't allow it to be cleared, and they are sure that they will return it back to Nigeria. So we're forced to actually work with the Chinese apps, and most professors too, they don't even trust the plant you are bringing, whether it has some activity or some ethnobotanical usage of what you are using it for. So it's kind of very, very complicated to bring a plant. It's very, very. I'm not even encouraging it for people for now.
So,
Okay.
apart from extraction and purifying compounds, do you do bioactivity in your lab?
Sir?
Hello? Apart from extraction, do you do biological activity in your lab?
Yeah, we do biological activity. We use some cell lines and
Yes.
animal study, and then Drosophila melanogaster to
Yes.
also assess some of the, especially if you are working with maybe neurological Parkinson. I'm working on Parkinson diseases, so of course we use so many models. But even with that, they don't allow us to stop at fraction level. They want a pure compound to be tested with, because those materials are also very, very expensive. So it's so difficult to say you want to report your work at fraction level. And
So
then
this is the point. This is the point I want to bring home. Okay, purifying compounds is not a problem. You can get pure. Being pure doesn't mean that it is new. Okay, so you can purify your compounds, and once you have your pure compounds, you can always do bioactivity.
Yeah.
There are compounds whose biological activities have never been done. So you can do it and still publish your paper in a good journal. My professor always told me,
that's
even
what
if you don't,
we are told.
yeah, my prof always told, but even if you don't get new compounds, you can still do bioactivity on a known compound. Maybe this compound, someone tested it against diabetes, but you come with antibacterial activity or cytotoxic activity. And there are journals that are just focusing on bioactivities. Yes, there are many journals where you will not publish a known compound. You have to have a new compound. So it is not all lost. Yeah, just purify your compounds. Because if you cannot purify your compounds and have pure compounds, you cannot graduate.
Exactly, at all.
Yes. But you have to get pure compounds, known or unknown. Get pure compounds, then do bioactivity. Then you can publish in journals such as ethnopharmacology. Okay? Let's say a particular plant has been used traditionally for diabetes, cancer, antibacterial property. When people have some alimentary problems, you went somewhere and ate something, and you keep you have a running stomach. So people have used it traditionally, but the bioactive constituents have never been isolated. Then when you are able to isolate the pure compound, yet, yes, they are known, but you obtained pure compounds and determine their activity. And you found out that, oh, this particular compound number 12, whose name is this? This compound indicated strong antibacterial activity. This therefore ratifies, confirms, underscores the use of this plant against diarrhea. You publish a good paper in Journal of Ethopharmacology. I think it's 3.8 or 4 there. So that too is important. If you cannot get pure compounds, there is a problem. Even me in my lab, I may chase you. I'll say, this is a lazy student.
Okay.
Yeah.
Thank you so much.
Yes.
Thank you so much. Wow. Today's presentation is full of knowledge. Yeah. Thank you, everybody. Thank you, Dr. Sakah Kaunda, for your time. Thank you, participants, for your time. Thank you very much. So right now it's about 9:30. So we will be rounding up the program. On behalf of OAAD, we say a very big thank you to Dr. Sakah Kaunda and also the participants for creating time to attend this program, this webinar. So thank you so much for coming around, and we will be rounding up the program now.
Thank you.
So,
thank you very much.
Yes, you're welcome.
Yeah.
Yes. So,
very much for your moderation, for guiding us, helping us, and for setting up this platform. Many people don't know the background activity that you are engaged in to make this a success. So, Dr. Layemi, I want to appreciate you very much. And
thank you.
Continue with OAAD, even if you are not seeing fruits now. But what you are doing, God willing, may one day help African kids who are probably in their primary school today. Yes.
Amen.
So we're looking forward to greater days when OAD will be winning grants, research grants, and we'll be establishing big laboratories back in Africa, headquarters in Nairobi, doing natural products chemistry. So thank you so much for pioneering this organization and for giving yourself fully to this calling. Thank you very much.
Thank you. Thank you so much. Thank you. Thank you. So I wish everybody safe trip back home because you have traveled all the way from your research lab, your activities up to this webinar platform. So we are grateful. Have a lovely night's rest. Thank you.
Thank you.
Yeah.